Hello, everyone. Today we have here Professor Jiang to talk to us about reinforcement learning and how it's applied within video games. So take it away.
Yeah. Hello, everyone. I'm Nan Jiang. I'm an assistant professor at UIUC, and my research is in machine learning with a special focus on reinforcement learning. And today is my great pleasure to talk here at Chick Tech Talk. And I would like to just to give you some brief idea of what reinforcement learning is, and mostly using video games as really like illustrating examples. But then we'll also talk a little bit about how RL, which stands for reinforcement learning, can be applied to more real world problems. Okay, so I think the wrong example I'll be using is like how do you like teach a computer to play video games, right? So I think many of you will probably have like more experience in video game playing than I do, and you may have seen like the computer AI playing the game maybe in a pretty horrible way in some of the games, and you may wonder like whether they can like the AIs can play the game like more intelligently. Right, so it turns out that machine learning offers quite many different solutions to enabling this. And let's maybe start with the simplest one, right? So well, before that, let's first introduce some notations and terminologies that we often use to when we formulate game playing as sort of a machine learning problem. Right, so let's say we're playing like Super Mario, and we have a game screen which tells us what's the current configuration of things, like where your character is, where the enemies are, how many lives do you have, like things like that, right? So we call this the state of the game, okay? And at the current state, you're going to take an action where the action basically corresponds to what button do you push, do you press on your game controller at the current time step. And then you may get what we call an immediate reward, for example, in terms of a game score. Let's say like you kill the enemy and you get like +20 scores. And then you're going to transition to the next game screen. And this transition can be random. For example, the system, the game simulator may decide to spawn some enemies like randomly, or they're all just kinds of like a random and unpredictable events going on in the environment. So like, where you're going to land at the next frame can be, can look random. Okay, so this, then you go to the next state, and then you take the action again, you go to the next state, and so on and so forth. And this repeats for a lot of steps, and then that's like, a game. Okay, and the goal, if you want to teach a computer to play a game, essentially the goal is that you want the computer to learn what we call a policy. Okay, so a policy would be a mapping from states to actions. Basically, the computer will look at the screen, which is the state, and there's a functional mapping that maps the state to a particular action, right? Maybe it looks at the state, and maybe the enemy is close by and like just near me, then maybe there's a rule that tells me like I should fire, right? Or maybe the enemy is too strong, I can't beat him, maybe I should jump, right? So it's like essentially like a set of rules that tells you like what action do you want to take under which state. And the problem here is like, can we teach an AI agent to play the game? And more formally, you can think of it as like learn a policy that helps the agent or helps the character earn as many game points as possible within a period of time. Okay. So here is a simple strategy that you can use, and it actually works. It's called a supervised learning approach. What you can do is that you can play the game yourself, and here I'm assuming that you're a pretty good player. Okay, so you play the game yourself and record the entire process of your like playing. Okay, so not only you need to record all the game screens, you also need to record like what kind of buttons have you pressed like during the gameplay. Okay, and you will be able to pair like game screen with the button you pressed, game screen button you press, right? And after you play whatever like hours of the game, you get a lot of like these pairs, like presumably like thousands or even like millions of such pairs that what we call state action, state action, state action. Okay, what then you do is that you use this as what we call a supervised learning data set. And use it to train a policy, right? Essentially, you just directly feed this data set to the computer and use a standard machine learning algorithm that learns that tries to predict what your action would be given the current state. And typically, the state-of-the-art approach in machine learning for these kind of tasks, as some of you may have heard of, is like what we call deep learning, or using deep neural network as the functional form to model this mapping. Okay, so this is fine. But here is a caveat, right? What if I'm a terrible player, right? Maybe I'm a terrible player, but I'm very good at programming. So I still want to create a very good agent, but I can't show the computer how to play, but I want the computer to figure out how to play itself, right? So is this still possible? Well, that's what reinforcement learning does. Essentially, reinforcement learning is a paradigm that allows the computer to learn by itself via trials and errors. Okay, so I'll give you sort of like a conceptual sort of depiction and very cartoon sort of illustration of how RL could work. Like RL can work in many different ways, and what I showed you below is a very concrete approach that is just easier to explain. So conceptually, like the question you need to answer is, I'm in a state, how should I act, right? What kind of button should I press? And in the previous supervised learning approach, we know that we get the signal just from the human. The human is the teacher and tells the computer, you should press this, right? But what if like I don't have the signal, I don't have a teacher? Well, the sort of naive idea is that I can try different options, right? So I know like at the current state, all I can do is like, move forward, backward, jump, fire, or something like maybe there are 10 options in total. So conceptually, maybe I can try all of them. And what I do is that I can try each action. For example, this time I try the right action. And then after that, I can just, and maybe what happens is that whatever action you do at the current time step, you don't get any immediate like score signal. So you don't really know which one is really good. But what you can do is that you can, after you made that choice, you can just finish the game and look at how many points in total you have got. And let's say maybe I try go right and then finish the game, I get like whatever number of points. Okay. And then what you can imagine is that maybe you can just go back to that exact state and try a different action and finish the game again this time and see how many points do you get, right? And you can compare the number of points you get when you, where the only difference is that at that point time step, like you chose different actions, and maybe you can just decide that the action that gives you the most points is the best action. Maybe, right? So there's a lot of caveats in this reasoning, which I'll talk about in a minute. And what you can do is that then you can just pair the state with the action that you have decided, right? Essentially, you become a teacher of yourself after trying different options, right? And then you can just use the same pipeline as before, train a deep neural net to get a new policy. And I should mention that, this process you can actually iterate like multiple times, because when I say you finish the game, you have to use a like default gameplay strategy to finish the game, right? So after you improved, you have a new policy. You can use that new policy as your default strategy to finish the game, which presumably would be a better approximation of what the optimal gameplay should be. And so you can like keep improving over yourself like this. Okay, so there, like as I said, like that's highly conceptual. It's not even like a an actual algorithm you can run. So you may have many questions. For example, like we after an action we only play the entire game. We play the entire game once to the end, and that just gives us like one data point. That seems extremely wasteful, right? After I finish the entire game, I just get a number, like the total number of points I get. But during that playing, I see all the state's actions, all the state's actions. Can I learn from them, right? So that's a natural question. And the other question is, the conceptual framework I described is like, after you try this strategy, you finish the game, and then you go back, reverse time, and travel back in time, and reproduce exactly the same situation as before, right? But as you can imagine, like, this is maybe doable in a simulator, but if you want to apply the framework to more real world problems, there's no resetting button in the real world, right? So how can you avoid this? Also, when you see that an action leads to fewer game points, maybe it's not because that action is bad. Maybe it's just because the way that you finish the game is bad, such that a very brilliant move may look terrible just because, the way you finish it, it doesn't really, review the true value of that brilliant move, right? So how can you address that? Okay, so I'm not going into any details here, and I will not actually be answering all these questions, but just to let you know that the way we answer all these questions is to come up with, a mathematical framework called markup decision process, and also related to what we call dynamic programming, which is a rigorous and flexible mathematical framework where we can actually study and answer all these sort of like intuitive questions you may have. And some of the questions that seem very naive and intuitive to you, but we're still answering that like after, I don't know, like 30 years of development in this field. Okay, so I want to then, I described sort of like a cartoon picture of how you can use this to play games. But let me just show you how we have actually made some progress in actually play some serious game, right? So I think some of you probably know, like, Deep Blue beat world champion in chess in 1990s, but that algorithm uses like alpha beta search, like some form of exhaustive search. It's not really learning, right? At that time, actually, I still remember myself clearly because I grew up in that age. Is the game of Go is order of magnitude more complex than chess, and at that time, no one believes that we'll be able to solve Go in near future. Okay, it's just like everyone thinks like it's too difficult. Chess is somewhat manageable, but the strategy you use for chess, if you directly apply to Go, it's just like a non-starter. Okay, and to everyone's surprise, in 2016, we have this AlphaGo algorithm from DeepMind that beats a human Go master. And what it does is a combination of the two techniques that we talked about previously, right? What it does is that it first warmed up the policy using a supervised learning approach by having the computer reading like all the historical games between human masters that the researchers can ever find to find a decent policy to start with. And then it improves upon itself using reinforcement learning to become like even better than the best human player. What's really interesting is that 1 year later, we have a new version of AlphaGo called AlphaGo Zero that actually completely get away with like all the supervised learning data. Because what they find is that if you train the AI agent using the human master like gameplay records, it actually puts a restriction on the way that the AI thinks, right? So the AI only thinks in terms of like, whenever you face a game configuration, a particular game board, it starts to think about, oh, what human masters have kind of moves human masters have played, and I'm gonna focus on that particular set of possible moves. But there may be some potentially very good move that no one in the history ever thought about. And the AI is actually discouraged to think about these like very normal moves if you feed it with like tons of like historical human data. So what the researchers decided is that they just like start from scratch, don't give it any human data, and just try to improve upon yourself. And again, to everyone's surprise, this time they become even better than last time and just sweep like all the master level human players like easily. And the other, I think, very impressive thing that's worth mentioning is that this is a very generic framework that is not really specialized to the game of Go anyway. And with minor tweaks in the algorithm, this framework is shown to be able to play chess, shogi, or whatever. Whenever you have a game that you can self-play to improve your skill, this framework seems very, very powerful. Okay, so to conclude the talk, we've been talking about like games all the way, but really like reinforcement learning holds a great promise to solve many important real world problems. And but there are many limitations and challenges to achieving that goal. In particular, the limitation of the current reinforcement learning algorithms and research is that almost all the success stories we have heard require the availability of a simulator, right? So if you have a simulator, what's really nice is that you can just keep playing with yourself and generate like infinite amount of data as long as your computation allows, right? And also in the simulator, you can try anything you want and it won't generate any real consequence. Like say in a simulator, you learn to play a car racing game. I can guarantee you like 99% of the time that all those training algorithms, like before they actually mastered how to actually like drive a car, they'll crash the car like maybe millions of times. And by millions, I'm not exaggerating anyway. It's literally like crashing the car millions of times. But you can't even like afford to do that once if you are driving a real car, right? So that's a lot of challenges, and that's precisely many of us in the research community are the sort of research questions that many of us in the research community are trying to address. And the reason we want to address this is because we really want to apply reinforcement learning to many real world problems whenever it is a dynamical system and you make a sequence of adaptive decisions to achieve some long-term goal. For example, you have robotics, you have chatbot, right? So let's say you have automated customer service where a customer comes and you can interact with the chatbot and have like, have a conversation where after multiple conversations, where each sentence you can think of as an action, you may help the customer to resolve his or her issues. We have personal assistant that helps you use your computer in a better and easier way. We also have online education where the computer program may be able to show personalized and adaptive contents to the student depending on the computer's understanding of how well the student is learning. So yeah, so that's where we're looking into in the future. And with that, this concludes my my slides, and I'll be happy to take any questions and discuss related stuff.
Great, thank you. One question I had was, so whether it be teaching reinforcement learning for Go or teaching a car to drive, how much time goes into teaching the algorithm to like learn that? Like, I'm sure it'll probably get quicker as time goes on, but currently, like, what is
Yeah, so this really depends, and it varies a lot across different types of games, and depending on the algorithm details you use, like everything can like differs a lot. And the other thing is that we don't, in terms of like time, or I think the question you're asking is essentially what we call like a learning efficiency question, and it's actually a little bit more nuanced. We usually measure learning efficiency using two different metrics. One we call it computational complexity, and one we call it sample complexity. So computational complexity is like, how many games do I need to play before I can learn to master this, right? And that's sample complexity. Computational complexity is like the total amount of computation I've incurred during this process. So if you ask like the current time, it's typically about like computational complexity. So I don't really have a good answer to it, but to my knowledge, for example, the AlphaGo Zero, it takes at least a few days to maybe 10 days or weeks to train on a lot of like computational resources. So this is actually one of the key bottlenecks of the current research is it's reinforcement learning. The modern algorithms are very, very computationally expensive. Like I mean, I can easily burn like thousands of dollars of cloud computing credit just to run some standard experiments in my paper. And that causes another issue is part of the reason that this is computationally expensive is because it's sample expensive, means that you have to play the game many, many times. And if you think about what that means in the real world, it means that, you have to get tons of real world experience, do a lot of trials and errors before you master a skill. And that can be even more problematic if you think about like real world applications.
Okay, kind of off of that, what are some like issues or criticisms that exist like within the field? So maybe applications of reinforcement learning outside of video gaming and like the testing data and like things like that.
Yeah, so I think I've mentioned a few criticism, already. Like, our current success heavily relies on the availability of a simulator, whereas our algorithms are not guaranteed to be safe if you use it in the real world, and also it's what we call sample inefficient. That is, it requires a lot of interactions with the system before it can learn. But that's merely just a small portion of the criticism and challenges that we have. There are others, like for example, when you think of like learning a policy, you can think of it as like learning a skill or learning a problem-solving skill. And what people often find is that the skill we learn is by these RL algorithms are not really generalizable, right? You change the environment a little bit, and your problem-solving skill just completely breaks down. It only works exactly for the version of the environment that it is trained on. So there's that problem, generalizability. There's other problems. For example, this is a very tricky one. So for example, which we call the reward design problem, right? So if you think about the game playing example, what we call the reward there is the game points you get. So we say we want you to play the game really well, but we actually don't know how to express the idea of like play the game well. So we use a proxy. So if you get enough points, then I'm happy, right? And you find these like very weird situations where computers get to like exploit the loopholes of the game mechanism. Like you have a racing game and the computer figures out that if you just like circle around, like, go in circle in a small place, and it just gets as many points as possible. But clearly that's not the intention of the human designer, right? We don't want you to exploit these loopholes. We just want you to, play the game. But what does even like playing the game mean? How do you convey that to the computer, right? You have to design this reward function, but it turns out that to be a very difficult task. And yeah, I think these are like some of the only a sample of the challenges and criticism we currently have.
Yeah, so one of the other questions we had was, what do you think the future of reinforcement learning will look like? Like, do you feel like it'll get better in real world applications, or do you have like any hopes that it'll achieve something else in the future?
Yeah, I think that's a good question. So it really depends, and I'm somewhat optimistic. Otherwise, I wouldn't be staying in this field and keep pushing the front. But I think the reason I'm optimistic about real world applications is that more and more people are taking this more seriously. So what's funny is that if you look back maybe 5 years ago, if you look at what the reinforcement learning research community is doing, 95% of the community is working on playing games better, period. And no one cares about anything else. And as I mentioned, there are tons of challenges to be addressed if you want RL to be applied to real world problems other than video games. I mean, of course, video games are a great benchmark and test bed for testing some of the basic ideas we have. But to take those ideas and make them applicable to real world problems, there's a huge gap there, and that needs to be closed. And what's really good is that now I think many more people are looking at like closing this gap, and I'm optimistic because that's just what's happening like within the last 5 years, which is a really short amount of time. If you look at things in terms of like scientific progress. So hopefully will address many of these challenges and make reinforcement learning applicable to many real world tasks. And the other reason is that I think some of the problems are easier than the others. For example, in terms of like chatbot or like these personal assistant, like whenever things are digital, because whenever things are digital, we have well-logged data, and also, making a decision doesn't really, hurt much in some sense, right? If you have a chatbot, as long as it doesn't throw out dirty words, if it like doesn't really address your question, you can always like say, oh, if the conversation went on after 15 minutes and the customer is unsatisfied, she can always call like a human customer service, right? So and there you can more comfortably let the algorithms do trial and error and to learn. So I think that there are definitely real opportunities, and I do believe that in the future we'll see more and more applications of RL.
Yeah, so to kind of close off the talk, for any students that may be interested in getting into reinforcement learning or machine learning in general, what would you recommend they do, or what skills do you feel like they should have before coming into this?
Yeah, I mean, I think that's a good question. And in general, machine learning is a discipline that heavily relies on mathematical background and programming background. So those two are, obviously the most important things, right? So, for example, if you're a freshman or sophomore student, then you should really pay attention to your calculus and linear algebra course. And actually, probability and statistics is as important, or if not more important, for machine learning and also reinforcement learning. And some level of programming is also very important. But other than that, I think it's the most important thing is just to willing to experiment with things, dig into papers, and really maintain a level of curiosity and have the ability to find questions and answer questions yourself. I mean, which is somewhat generic for research.
Okay, thank you so much, Professor Jiang, for talking to us today about your presentation, and thank you to everyone else who came.
Yep, thanks for having me here.